We are now recording. Let's get the slide set up and we're ready to go. Sort of. Okay. Now, we were talking, any questions, anything we've covered so far? Okay. We were talking last time about separation of variables, and they do have a little warning right about the middle of page 49, section 2.2, chapter 2, first order differential equations, and 2.2 is separable variables, okay? And this warning is this one. You might, in some circumstances, lose a solution, okay? You got something? Okay.
Partial credit for any of them?
No. And that's why.
Number 7 was a long one.
Really? Okay. So that's why you turned in the work out. Good.
Yeah.
Good. I appreciate that.
No, I did work for all of them just to make sure.
Yeah.
Some messed it up.
Right.
Some partial credit.
All right. Yeah. I give as much as I can get away with. Okay. So if I see you're on the right track, I do. I do look to get the full credit, you have to have the right solution. But if you're.
There was a lot of trade identities.
Right.
Stuff, just making sure you knew.
Yeah. Is that the one with the logs and the cosines and all that? Yeah.
You get a bunch just like
Yeah.
sine ln x, sine ln x plus.
Yeah.
like
It was a miserable problem. Where I used their materials to do. I don't make them up on my own because mine are always too hard. But when I saw that when I was working out later, I went, "Oh, did I ask this question?" Because I didn't think it was going to be quite as awful as it was.
There's just a lot of identities.
What's that?
There's just a lot of identities and figuring out how to derive it.
Yeah, but it was a good review of Cal 1, Cal 2, Cal 3. Yeah, okay.
That's what I looked up just to make sure I was doing all the
Right.
identities and make sure I knew them all when I was doing 60.
Good deal. I think that my view of testing, it should be part of the learning experience, not separate from it. You know, it's not just now you've learned it. We'll see how well you learned it. I think it should be part of the.
Exam in here, is there another take?
What's that?
Is our final exam taken?
Yeah, it will be.
If you did one of those on the exam in here, I feel like that might be a little long.
Yeah. Well, the only trouble with that is it's a much shorter window that you have to turn it in. But if you need more time, I can give you an incomplete, and then as soon as you get it turned in, I can do it. But because final exam week is, I think, 2 days or 3 days in the summer. So I'll give it to you last day of class, so you got to get it back to me the next, whenever the final is. So it's sometime the next week. So I'll try to keep it a little bit shorter and fewer of those type of questions. So far, it's worked out okay. All right, like I was talking about before, sometimes you might wind up losing a solution. That's what they call this subtopic here. And here's an example of that. Let's say we have, and this is generic, it's not anything specific, dy dx, and the pen is really slow. Oh! In the slideshow. Okay, there. Really nice. Is equal to g of x, h of y. Okay? Now that looks like a classic one to do by separation of variables, right? Now, before you do that though, if there's some value of y that makes the h of y 0, then the right-hand side is 0. The left-hand side would have to be 0, so that would be a constant function, okay? Whatever value y that would be, where that would be 0, you would have a constant function at that y, okay? Now, do your separation of variables, okay? How would you do that? Okay, we'll multiply by dx and divide by your h of y. Okay? And really, Mathematicians hate it when you say multiply by dx, but that's really what you're doing, or it seems that way. Write it in differential form. These go out. So now you have dy. Oh, I forgot to divide by h of y over here. Okay. dy over h of y is equal to g of x dx. Okay? Now, what happens now to that value of y that makes h of y go to 0? Over there, it's perfectly fine. It gave you a constant, how about here? Undefined. You never find it this way. So a lot of these, anytime that might be occurring, you have to, before you do that, discover the y here, or look for it up there, and see if that does give you a solution. And in this case, it would, whatever that y is. All right. Okay, we're right. Yeah. All right, good deal. So, that was just a little warning before we move on to the next example, example 3, which there's, well, I won't say anything else. Okay, here is dy dx is equal to y squared minus 4. Okay? What can you tell me about that differential equation?
No x.
It's what? There's no x on the right-hand side. So that had a sort of a special name, autonomous. Okay? Also, obviously, a ordinary differential equation, no partials. Linear differential equation, the whole chapter is linear.
The y squared.
And you got a y squared, which makes it, okay, right, I'm sorry. Yeah, I'm saying linear. First order differential equation, which is the whole chapter is first order and nonlinear. You're absolutely right. Okay? How would you go about solving this? Okay. Multiply by dx and divide by y squared minus 4. Okay? Okay, so that gives you dy over y squared minus 4 is equal to dx. And then you do what? Integrate both sides. Whoa! How in the world can we integrate that? Any technique come to mind? I don't think so. It would be if there was a 2y up here, or just a y up here. Because, see, the derivative of this would be 2y. If it just was a y minus 4, ln would be perfect. ln of y minus 4. That would be great. Not with the squared out there. So what would be our approach? Oh, no, we have to know how to do this course? Yeah, unfortunately. Remember? Say again. Okay, you hit 2 of the methods, but unfortunately neither will work. Substitution has the same problem that ln would have. You need the derivative of this up here somehow, and you don't have it. Okay, you can use a trig substitution, and that will work. There is one other technique. And say again? Partial fractions will also work. And which one you use is sort of up to you. I want to say you'll get the same answers. They may not look like the same answers, but they will. So let's do partial fractions. Unless you remember what the trig substitution is. Do you remember that one? It would be tangent requires it to be a plus.
What's the other ones?
Like a secant. Secant. It would need to be a secant one, and that has multiple pieces of it and stuff, and I think you could do it that way.
Wouldn't it basically it'd be like a 1/2 times whatever your tangent is?
You mean when you do that? Yeah, because of the 4. You mean, yeah. Yeah, you would have that, and then there's all sorts of things. Another option, of course, is look it up in a table. That would be perfectly fine. But let's go ahead and do it by partial fractions. Sounds like that might need a little review. How do we do partial fractions? What we're doing is we have a fractional form here, 1 over y squared minus 4. Okay? A over y minus 2 plus b over y plus 2. Now that should work, shouldn't it? Okay. Does anyone, and by the way, this obviously is y plus 2 times y minus 2. Y minus 2, I can't write. Let me clean that up some. Okay. Oh, not that. That. Okay. Y minus 2. Okay. Do you remember the next step for this? Okay. That's certainly one way to do it. That's the hard-working way, which is good. You know, a little easier way is multiply both sides of the equation by the least common denominator, because that's an equation, isn't it? So what is it? Okay. And what was the left-hand side? No, left-hand side. The other left. Okay, you're multiplying by that. So what does it leave you with? 1. Okay, good. Hard. Okay. And on the right-hand side, you just were saying a times y plus 2 plus b times y minus 2. Everybody see that? What you did? Multiply both sides by this. So this denominator goes away. You're left with just the numerator. Multiplying this one by this. The y minus 2's go out, and you're left with a times y plus 2. Multiplying this one by that. Y plus 2's go out, and you're left with a times y minus 2. So now you got rid of the denominator, so I'm a little happier here. And the next is a really, and by the way, I'm going to go back. You're going to find that my first statement, the logs won't work. Actually, our answers will be logs, but just not the log of this. Okay. So, just to clear it up so you won't say, I told you so. Okay. So, it always seems like an unfair thing to do, but here's the easiest way to solve that. Anyone know? But so far, it's the easiest I found. That's it, exactly. This should be true for all y, so why don't we have y is equal to negative 2 and see what we get here? What's the left-hand side become? 1. It doesn't change. The first term goes to 0. And the second term goes to negative 4b. So therefore, what's b? Is equal to negative 1/4. Okay? Now, that works so well. What might you try also? Second, y equal to 2. What does the left-hand side become? 1 is equal to 4a. And the second term? 0. So that produces a is equal to 1/4. Okay? So now we can change our integrand here to the integral of dy. Let me change that. Okay. Integral of, I'm going to do the a first. Okay? I'm changing this to this where a is 1/4. I'm going to put the 1/4 out front. 1/4 the integral of dy over y minus 2 minus 1/4 the integral of dy over y plus 2. Okay? What will that lead to as a solution?
minus 1
And by the way, you always should probably put those in absolute values. Why?
it's positive all the way.
Yes, you cannot take the log of 0 or a negative number. Okay? Minus 1/4 the log of y plus 2. Okay? Now, and then you'd probably have a plus c in there, though I'd be tempted to make it a plus log c, but we won't mess with that right now. Well, we should, I guess. Let's call it plus ln of c. Okay? Does anyone remember from your rules of logarithms, I need more room to write, so is it all right to go up and erase this at the top because I've already used it? Put it in. Bought a t-shirt, so let's get that out of there. Okay. What's another way we could write that first term? The ln of what? No, you can't do that. Y minus 2 to the 1/4 power. Remember that? You can take a coefficient of a log and move it to the exponent of the argument. Yes, and then this will be, and you can either do minus or plus. Let's go and do it with minus, the ln of y plus 2 to the 1/4 power. I'm wondering if I should have, okay, made that c to the 1/4, which would be fine. That's just a constant, so I could do anything I want to. And remember, and even now, even more important, we have the absolute values there, because you can't take the 4th root, an even root, of a negative number either. So, do you remember another property of logarithms we could use on the left-hand side, or in the first two terms? Yes, exactly. That's what I'm talking about. The ln of the quotient of these two. Okay? And that was the absolute value of y minus 2 over absolute value of y plus 2. So why don't we just make the whole absolute value, okay, and do it all to the 1/4 power, okay, because they're the same thing. So we're doing all sorts of things, plus ln c. And now we can do something else. The sum of two logs is the log of the product. Okay, multiply them. So that would be the log of c times absolute value y minus 2 over y plus 2, the 4th root of that. Okay, I like to write it that way just as well as that. So anyway, all that to do, and okay. How have I forgot? Oh, yeah. All that is the left-hand side, by the way. I haven't even started on the right-hand side. So, let's erase a little bit more. Okay. And we'll erase down here. And I'm going to backtrack something I just did. Let's erase all this stuff. Selected stuff. Okay. Okay. I'm going to back off because they did. And it was okay what we did, but let's not even mess with the C here. Okay? I've still got my right. No, I got my pen back. All right. Let's forget about the C here. Because we've got to do the right-hand side, and we can put our C there, and maybe it'll go better there. They suggest it will. It's perfectly okay to do it the way we did, but What's the right-hand side of this when you integrate that?
X.
This is just x. Now let's put our plus c, because they did. Okay? So this thing here is equal to x plus c. Okay? Now, do you really fall in love with ln's? Are they your favorite functions of all time?
I think it's just easy to remember.
What?
I just said it might be easy to remember.
What would? Yeah, ln's. But how could you undo an ln? I'll tell you, ln is not my favorite. My favorite is e. Because to take a derivative of e, you get itself. To take the integral of e, you get itself. I love e's. They're so easy to work with. Are e's related to ln's? Yes, they're inverses of each other. So let's take the e of both sides of this. Okay? E of this and e of that. Okay? Well, what does that give us? The e and the logs cancel each other out, basically. So you have absolute value of y minus 2 over y plus 2. And here's Warren. Okay? And that would be equal to, and I'm going to cheat a little bit here too, I hope y'all are okay with it, e to the x times e to the c. Right? Okay. Which e to the c is what? Just a constant. So we can change that and make it something else. K or C1 or something like that. But anyway, here is your solution. Oh, and by the way, e's are never negative, are they? So therefore, can we lose the absolute value signs? Yes, why not? Okay. So let's lose those, and we have c e to the x. Let's write it this way. Y minus 2 over y plus 2 is equal to c e to the x. And I can't think of any better way to express that.
Did you forget the 1/4?
I'm sorry?
You didn't put the 1/4 down.
Oh, wait, yeah, sorry. You're absolutely right. That's to the 1/4. So what I want to do now, this is to the 1/4 here, okay? So let's raise both sides to the 4th power. That gives you y minus 2 over y plus 1, plus 2, don't make up new numbers, is equal to, when you raise e to the c to the 4th power, that's just some constant, not the same c, but I'm going to use c. And this would then be e to the 4x, right? Okay, sorry. That's it. Thanks for picking up. I forgot my 1/4. Okay. So let me take out. Well, what I'll do is I'll put my 1/4 in here and then go to that. Okay. Now, it's not the same C, so go back and change this to a C1 or something else, you know, and then make that a C. Okay. No, I guess that's the C1, and that becomes your C. Well, maybe not quite, but close. Okay. Okay. Now, I'll look at this solution. And what do I have to exclude? What can you not have? Say again? Yeah, what value for what? Oh, y can never be -2. We'd have to put that in there. And that, otherwise that would be our solution, right? But, remember from the example we did before, that's why I left this up there, it's hard to read. Let me go back and wipe out the things I put in. Okay. Okay. All right. There was our original problem, right? Okay. Does this have any reason to exclude y equal -2?
2 squared minus 4 squared.
Yeah, but that's okay on the right-hand side, isn't it? Can't you have a 0 there? What does that tell you about the y function when the dy dx when y is equal to 0? Y is equal to 2. No, it's not undefined. It's 0. Didn't you just tell me? When you put in y equal 2 there, you get, or -2, you get 0. dy dx equals 0. When y is equal to -2, sorry, down here, then you have a slope of 0. Okay? That's perfectly fine. That's what, remember from before, we called a singular solution. Doesn't fit your family of solutions over here. It's a singular solution. And if you think back, this wasn't autonomous. We can do those little things. That would be that, they called it critical values or something like that. That would be right there. Y is equal to 2 is going to be in there. Everything else has to work around it. Okay? And indeed it does. And by the way, y is equal to +2 will give you the same horizontal slope. But that's okay there. You know, because you get that there. When y is equal to +2, you have 0 is equal to c e to the 4x. Or is that okay? That would only be true if c were 0. Right? Because e to the 4x is always exponential functions are always positive, never negative, never 0. So that would mean, for that one to work, c would have to be 0, but that would be fine. C can't be 0. C can be any constant. So that when you get through your solution, your family of solutions, the one down here, though, you don't get in your family of solutions. You have to remember to go back and say, or, so this is your family of solutions, and then your singular solution, or y is equal to -2. That will work up here. Okay? And dy dx would then be 0. So that would be okay. Now I did say something not quite right there. I used faulty logic there. I didn't take it far enough. When you remove the absolute value bars, that then introduces over here, this is plus or minus. Sorry about that. This becomes a plus or minus. So now what I said before, that E is never negative, but if you have a minus sign in front of it, it is. So let's go back to that. I don't know what to erase next. I think I'll erase this because we've already finished with that. Okay. Probably erase more than I should, but it's okay. All right. So this gives us wow. Y minus 2 is equal to plus or minus c e to the 4x times y plus 2. Right? Right. Okay. Now, what we're going to do here is multiply this through, and this will be y minus 2. This this gets me, this is just the algebra part. That would be y plus or minus c e to the 4x plus or minus 2c e to the 4x. Now I'll get the y terms together. Okay. No. Yeah. Subtract a y from this side. That's not working right. Sorry, I wrote it down wrong. Okay. That's, let me erase that part too. Sorry about this. These parts can take too long. Okay. Trying to get the same, what we had is correct, but it's phrased differently in the book, so let me try to do it like they had it. Y times this, that would be plus or minus cy e to the 4x plus or minus 2c e to the 4x. So you multiply these two together and multiply those two together. So now we're going to add or subtract, and let's do them separately. Let's just first do the pluses, okay? Forget the minuses for now, okay? Okay. All right. Oh, wait, let me erase this too. All right, now we're going to subtract cy e to the 4x from this side and over here, minus cy e to the 4x, and we'll add 2, and we'll add 2. Okay, need to erase some more stuff. Okay. By the way, this is example 3 on the bottom of page 489, top of page 50. And it's the differential equation part was real easy. Getting the answer is proving to be a bigger pain in the neck or some other body part. Okay, so let's see. Okay, all right. So yeah, so when you add those two together, you get y minus cy e to the 4x. Okay, the 2's go out, these go out, equal to 2c e to the 4x plus 2. But you could factor out a 2 if you wanted to. Now factor out the y. Well, I want to do that. That'd be y times 1 minus c e to the 4x. And this will be is equal to 2 times c e to the 4x plus 1. Okay? Then divide both sides by this. What we're getting is an explicit solution for y, which seems like a lot of work to make that happen. So this will be 1 minus c e to the 4x. Okay. And here's Monica, right? All right. And Monica is breaking the right side of the room to this and moving to the left. Okay, she's going to be by herself over there against all odds. Okay. Now, what we have here is these go away. Here's your solution. Y is equal to 2, and I'm going to reverse them to make them look better. 1 plus c e to the 4x over 1 minus c e to the 4x. Okay. Now, what would happen if you put the minus sign in there rather than plus? So you did the minus here, then you'd have minus here, and you have plus here, minus, and basically you wind up with the same solution. I'm not going to do it. I don't have enough room for it, but that's the solution we get. Let me erase that last part so it's not confusing. I just looked at it and got confused. Okay. But that's what got us there. So there's your solution. Now, in this solution, we take a look at that. And is it nearly as obvious? Okay. So c e to the 4x can't equal 1 here. So that means e to the 4x can't equal can't equal 1 over c. Okay? And e to the 4x, which you could then take a log of both sides and go. And it's a lot less clear that that's limiting. That looks like any x will do, but not quite. Okay? And so our earlier one was pretty obvious that you can't have a y equals minus 2. This one is not nearly as obvious, except for this. No, that wouldn't work either. But that's why I didn't want to really go to that form. But they said if we factor the right-hand side of the differential equation, okay, we already have done that. You see that y is equal to 2 or minus 2 are constant equilibrium solutions. However, y is equal to 2 would only be true when this is 1. And y is equal to minus 2 when that is negative 1. And you have to do a lot more head scratching to see what would, if there's a problem there, and y is equal to negative 2 would be a problem. But it is okay up there, it's just not down here. Therefore, we lost that solution when we got there. But looking at that, it's not particularly obvious that that's going to be an issue, except that this thing can't be 0, so e to the 4x can't be 1 over c. Right? We said that. This can't be 0, so divide both sides. Add this to both. 1 can't be equal to that. Okay? Divide that by c. E to the 4x can't be 1 over c. Well, obviously c can't be 0 then. Okay? Because it can't be 1. Okay? Certainly can't be 0. But a c equals 0 will work when your y is equal to negative 2. So that is your lost solution, which would be a singular, is that what they call it? Yeah, singular solution. A lot of blah, blah, blah for, you got the solution, that's the main part. There's your one parameter family. You just have to remind yourself, look at the original equation, see if there's anything that might be excluded there, and be sure to put it back in. Now, that can all be eliminated if you do an initial value problem. Because then you'd specify, now you're only looking at one value for C. You don't have to worry about the values that you may or may not be able to use. You're only looking at one. So here's one. E to the 2y minus y cosine x. This is looking good already, isn't it? Dy dx is equal to e to the y sine 2x. Okay? Given the condition that y of 0 is equal to 0. Okay? Now, anyone want to classify that differential equation for me? Non-linear for sure. You got e to the 2y, that will wipe out, and e to the y, that's certainly going to wipe it out from being linear. Ordinary, of course, and first order. So, wow, what a function. How, is there any way we can solve that thing? Separate the variables, because you notice here, this factor is only a factor of a function of y. This is only a function of x. This is only a function of y. That's only a function of x. You can separate these two by writing them in differential form, and you've got it knocked. So you want to do it 1 step, 2 step, 3 step. How many you want to do?
You're going to divide by k sine x, multiply by dx, divide by dy.
Okay. I heard you multiply by dx, so I'll put the dx over here. I'm not writing them out as if I'm multiplying. Okay, what else?
Divide by ey.
Okay, put the ey over here. And divide by cosine x. I wrote it on both sides here. Okay. So, what does that give us? Yeah. So, let's go on and integrate. Well, maybe not. We might want to clean it up some first. So let's write it so it's a little more readable. E to the 2y minus y over e to the y. I don't think I need parentheses there. Okay. dy. Well, can't get my pen back. dy, that's your left-hand side, all separated for y. It's on the right-hand side. Sine of 2x over cosine x dx. Just looking ahead, does that look easily integrable? Does it even look like you might be able to find it in a table? I'm guessing not. So is there any way we can fiddle with the left-hand side to make it a little... All right. E to the 2y over e to the y minus y over... Is that what you said? Okay. dy. Okay. It's looking a little better, I would say. How about the right-hand side? No, it's not tangent. Too bad. Sorry. All right. We love our trig identities, though, don't we? Okay. What's the double angle formula? Huh? Okay. That's 2 times the sine of sine x cosine x. Ring a bell? No. Okay. Find you a, let's see, does this have them? Brief, okay. Functions. Yes. No, that's derivatives. Okay. Let's see if anywhere in here. Laplace transforms. No. I don't know if this book has it. You might just have to do, but that's your double angle formula for sine of 2x. Okay? Trust me, or do you want me to show it to you? Why it's true?
Can you show it?
Show it. Okay? Let's go back to this. What is the sine of alpha plus beta, say? Anyone remember what that is? Probably not, huh? Okay. I sure don't want to prove this one because this is a pain in the neck to prove. Can I tell it to you? Sine alpha cosine beta plus cosine alpha sine beta, if you had allowed enough room. Will you buy that? Okay, trust me on that one. All right. Now, let's say the alpha is equal to beta. What if alpha is equal to beta? Then what do we have up here? If alpha is equal to which? Doesn't matter which, to alpha. And if alpha is equal to beta, what do you have over here? Sine alpha, cosine alpha, plus cosine alpha, sine alpha. And that's 2 sine alpha, cosine alpha. So that's how we get that. Okay? Divide this by cosine x. I'm liking this side. Okay? dx. Okay? Cosines disappear. Okay, we got a little bit of work to do over here. What's this going to be? That's going to be, what do you say? E to the y? Perfect. That looks much better. Now, how about that one? Minus y over e to the y. That's still somewhat problematic, isn't it? Now, and this is not problematic here. 2 sine x dx. Okay. I'm not at all worried about this integration. This one's going to give me a little bit of a problem. What would you try? Well, one thing I would do, maybe, is rewrite it, and this may help a little bit. I'm going to go and write down the integral. Is that okay? Integral of e to the y dy. I'm going to split these up, minus the integral of, now, is it okay if I do this? Y times e to the minus y. Okay. That looks to me a little more palatable. Times the integral of 2x, 2 sine x dx. Doesn't it? What does this look like you could do? Okay? You like substitution, I can tell. Unfortunately, I don't see how it's going to help. If that were a 2y up here, yeah, that would be a great thing to substitute. It's not, it's just a minus 1. It was one of your guesses earlier that I rejected. By parts, integration by parts. Okay. Can I start erasing things because I'm running way out of room? Okay. So I'm going to, if it's okay, I'm going to erase this line. I hope I won't need it. I don't think I will, unless I made a stupid mistake and then I can't see what I did. These were just trying to convince you that my identity was right. Okay. And this was also doing that. And we ultimately got to here. Okay. So let's start with that first integral. What's the antiderivative of e to the y dy? E to y. I love e to y. Okay. E's. Okay. Now, we got to do our integration by parts here. What part do you want to be which? Okay. Sort of a strange way to say it. Remember how integration by parts goes? You let one of these be a u, let the other be a dv. Which one do you think you should let be a u and which should you let be a dv? Let me give you a hint. You want whatever you take to be u, the next line is going to do. Now we're going to write down the next line. Then du is equal to something and v is equal to something, right? Okay. So what you choose to be your u you want to make it be whatever it is. When you take a d of it, it's going to get simpler. Whatever you choose to be the dv, when you integrate it, you don't want it to get any too much more complicated. Does that give you a hint? Yes, let u be the y, okay, and dv be the e to the minus v. I mean, and minus y, dy. You need the dy with that one. So what's du then? Dy, that's easy. See, it got simpler, okay? And what happens if you integrate your dv up there? That'll give you v on the left. What do you get on the right? Minus e to the minus y, okay? Perfect, right? Everybody see that? Take a derivative of it and you'll get exactly what you had up there, okay? Then what do we do with that? Once we have integrated by parts, the first preliminary steps here, what's your result of that? Now notice here we have a minus in front of all this, and what do you do once you have these pieces? How do you put them in place? Long time ago, right? Okay. What the result is, you do your u times v, that's outside an integral, minus the bottom line, v du. Now, you need a little reason why we can do that?
You just say just multiply it.
Second?
Just multiply dv and
The dv and u dv, right. The v du you multiply, and you integrate that part. Here's where all this comes from, folks. It's from the product rule. What if you have a function that is a function u times v? What happens if you take a derivative of that with respect to whatever variable you want to? What is the product rule? In fact, wouldn't that be u prime? Is that what you said? Okay. I'm going to write it as du. Is that okay? v du plus u dv. I'll just leave off this bottom part altogether, okay? Do you buy that as an expression in differential form of your product rule? Okay? Now, if you had rearranged this, u dv is equal to d of u v minus d of v du, right? Now integrate both sides. Okay? This is exactly what we have here, u dv. The integral of a perfect differential is just uv, and then the minus, and that's a v du. It doesn't look much like 1, but that's your v du. So you see, that's the rationale for integration by parts. Make sense? Okay. Can I erase that now? Because it's kind of getting in the way. Okay. So what we write now is the uv part, but you notice there's a minus sign in front, and your uv is y times a minus e to the right. So that minus becomes a plus y e to the minus y. Okay? Now, you have a minus from the subtraction down here. You had a minus in front, so far that's a plus. The integral of the bottom line here. But that has a minus sign in it. So that plus goes back to a minus. These signs will trip you up, okay, given a chance. And that will then be the integral of v du, which is, and I took the minus sign out, e to the minus y dy. Okay? Now, Want to go on and integrate the left-hand side too? Right-hand side too? Ooh, where did I write it? Oh, I erased it. No, there it is, down here. Okay, there it is. What's the integral of 2 sine x dx? Okay, you don't need 1/2. Pull the 2 out of the integral. Pull the 2 out completely. Okay? And what's the antiderivative of sine x dx? Negative cosine. So negative 2 cosine x. And we probably need a plus c in there somewhere. Okay, you don't need one on both sides. You don't need one when you do the integration by parts until you get it in. We put it over there with the x's. All right, we got e to the y here plus, if I can read my writing, y e to the minus y. And now we got to do that integral. What would that be? Say that again now. Okay, I heard something about a 0 and a cosine x. I didn't hear all of it. Huh?
Don't you have to keep your 2 in the cosine x? Because if you derive that...
Oh, up there? Is that what you're saying? Cosine x can't be 0, so therefore you have to eliminate your any values. Well, guess what? We're only interested where x is equal to 0. Cosine is not 0 there, so we're happy campers. Yeah, if we didn't have the initial value problem, big time you have to make, well, everywhere that, well, yeah, if you multiply by something times 0 on this side, you wipe out the differential equation altogether. So yeah, cosine x can't be 0, which means x can't be your half highs, right? So yeah, that would be an issue to begin with. If you had cosine x equals 0, you don't have a differential equation anymore. Okay, because it would be 0 is equal to whatever is on the right. And that can't be, and so that shows up when you divide by it. But this is an initial value problem. As long as that 0 doesn't make cosine 0, we're happy. We don't even care about the others. That's the thing I was saying. Don't care about those other solutions if you have that initial condition. Okay? We care, but we don't just care much. Okay? So, what was the integration of this one? Okay, e to the minus y. So that's, and it's a plus because this, when you integrate that, we give you a minus, you add a minus out front, so this would be e to the minus y. Okay? And that's equal to minus 2 cosine x plus c. All right? Now, yeah, you can probably make this a little simpler and other things, but guess what? All we're interested in is what our c is right now. Well, no, I guess we do need to make it simpler. That makes it e to the y plus 1 e to the minus y is equal to minus 2 cosine x plus c. That may not be the best way to do it, but it's fine with me. Okay, now let's plug in our initial condition. What does that give you? E to the 0 is, and y is equal to 0. E to the 0 is 1 plus, and y is equal to 0, that'll be a 1. E to the minus 0 would be 1, okay? So I think we got a 1 plus 1 on this side, okay? And cosine of 0 is 1, so that'll be a minus 2 plus c, okay? So hard math now, 1 plus 1 is 2 is equal to minus 2 plus c. Add 2 to both sides, and you get c is equal to 4. So our solution that we're interested in is this one. This one, okay? E to the y plus 1 e to the minus y is equal to 4 minus 2 cosine x. Okay, I just turned it around because I don't like leading off with a minus sign. Now, any way in the world you can see we can write that as an explicit solution of y? You know, like we did before, went through all that just to get y is equal to some function of x. What's your chances here? 2 chances.
Have to turn it into ln.
Say again? Yeah, you have to do, if you did that to each term, then you can spend a lot of time trying. What do they get in the book? I'm hoping, yeah, see? No way to write that explicitly, so our solution is e to the y, and they didn't do what I did there, so they leave it in this form. E to the y plus y e to the minus y plus e to the minus y is equal to, then they do that side, 4 minus 2 cosine x. They put the 4 in this one. That's it. So that's why most of the time I don't go to a lot of extra links, getting them y is explicit in terms of x. A lot of functions you just can't do it. And this is one of them. Okay? So separation, separable variables. I like separation of variables. They call it separable variables. Really neat, straightforward. Sometimes the integration gets to be a pain, but really it's the easy way to go. Now, they have a little blurb here on use of computers, and I'll let you read that because what they did here is rewrite your solution here, all your x's and y's, in other words, add this to both sides, make this a g, capital G of x and y, and then that's equal to c, okay? And that's your generic solution to that differential equation, okay, with this being this stuff plus 2 cosine x, that's your g of x, y, okay, equal to some constant. And when it's equal to 4, then you just plug that in, and you get a curve there of x and y that make that true, okay? They show c is equal to 2 in your book. They show a whole family of level curves in figure 2.2.2, and then they show the one that we had, c is equal to 4, as the blue curve in the figure below it, 2.2.3, and then show just one of the other curves for c is equal to 2. If you have the computer to do this, you're probably going to solve it with the computer. Okay, so let's go on. Now, let's go to another issue here that sort of combines the last two issues, okay, so to speak. What if we had this as a differential equation? dy dx is equal to x, y to the 1/2, and y of 0 is equal to 0. Okay? Now, they have told us before what this is. Let's us now finally solve the differential equation, not just trusting what they said before. Let's do that. What would that give us? First step. Or steps. Multiply by dx, so that'll put a dx over here. Wipe it out there. Say again? Not by dy, please. Then you have dy, x dy. Divide by your y term to get it over here, right? So divide by y to the 1/2. So it'll be dy over y to the 1/2. Okay. Got it? Separate the variables, because the y is on this side, x is on that side. Okay? The dx did it for the x's, dividing by the y to the square root of y over here. So, here's what we've got. Yeah, let's go on to this. Integral of dy over, okay. Again, I don't like radicals, and I don't like variables in denominators. So I always try to put it, this will be y to the minus 1/2 dy. By that, makes the integration so much easier, okay? And over here is equal to, oh boy, this is tough, integral of x dx, right? Now, how do you undo or do an antiderivative of y to the minus 1/2? Oh, wait, that was Cal 2. We're through with that. I passed it. I don't need to know that anymore. Okay. What would that be? Power function.
Is it -1/2 in the front?
No pi's in here. Okay. What you do, you take your variable, raise it. You know, when you differentiate, you lower the exponent. Now you raise it by 1. So that makes it y to the 1/2. But then you have to divide. When you're integrating, when you're differentiating, you multiply. Here you divide by 1/2, which is multiplying by 2. Okay? Sleight of hand. And what's this one? Really do the same thing. X to the what? X squared over 2. You raise that by 1, divide by that 2. Okay? Now, let's just check and see. What if you take the derivative of this? Take the derivative of this, you get 1/2 by 2, which is 1 times y to the minus 1/2. That's exactly what you got there, right? Take the derivative of this, 2 times 1/2 is 1 times x to the first power. So yes, you get that exactly. Okay? And here we put in our plus c. Okay? Now, you can fiddle around with this and make it y as a function of it. Let's just plug in our 0 here. When x is 0, y is 0. So this will be 2 times the square root of 0 is? No. Square root of 0 is?
1.
Square root of 0 is? 0. And 2 times 0 is 0. Is equal to? 0 plus c. So it looks like c is equal to 0. Okay? Now wait a minute. Okay? What we have here is 2 times y to the 1/2 is equal to x squared over 2. So if we did want to write this as an explicit solution of y, let's divide both sides by 2. So that makes a 4 over there. Y to the 1/2 is equal to x squared over 4. And then square both sides, and you get y is equal to x to the 4th over 16. Okay? Now, if you look in your book, it says it has at least 2 solutions. One of these is y is equal to 1 over 16 x to the 4th. Okay? And by the way, that fits your, with your c equals 0, that's perfectly fine. But it has another one, and that's from your original problem. And let me go back. Hate to do this, but I'm going to erase all that I did up here. Okay, there was our original problem. Except for that wasn't in there. And you see, again, we have to think this. When x is equal to 0 and y is equal to 0, you have your initial condition. So this is your singular case. dy dx is equal to 0. Okay? And dy dx equals 0 is the x-axis. Okay? That's it. It also fits the initial conditions of that. When x equals 0, y is equal to 0 there. But everywhere else, that doesn't fit. This does. When x equals 0, y is equal to 0, basically, all this work we did, basically kind of unnecessary. Because you just plug it in there, and you see that's your straight line, horizontal line, the x-axis, where x is equal to 0, y is equal to 0, is always 0. Okay? But this one works too. So both of those solutions work. Y is equal to 0 and y is equal to that, with c equals 0. If c were not 0, then that wouldn't work. X equals 0, then y is equal to c. It only works when c is equal to 0. Okay. All right. They do some other fiddling with that, and I'm not really sure if that would be all that instructive to do. What they do is take our solution down there and put the c in it, and determine that c has to equal to 0, which is what we said it was anyway. So I don't know. It seems like they go round and around to do a lot of extra work to get right back where we were. Okay. So, here's some bad news, folks. Okay? Sometimes when you're doing this integration, separation of variables, or separable variables, you're going to get something that looks like this. dy dx is equal to g of x with an initial condition of y at x0 is equal to y0. Pretty generic form there. Okay? Now, that looks like a pretty simple problem to do, right? Separate the variables, because this is not g of x and y, just g of x. So dy is equal to gx dx, writing in differential form or multiplying by dx, whichever you prefer. Integrate both sides, and you get y is equal to the integral of g of x dx plus c. Wait a minute. Why don't we go on and integrate? Well, wait a minute. What if you can't integrate? What if there's no, that is a function that is not integrable? And there are some of them out there, by the way. Okay? Then you have to leave it in integral form. Okay? Well, what do you do about your initial conditions? Well, when x, okay, when x is equal to x0, y is equal to y0. So let's make y0 equal to the integral of gx dx, and here's the catch, okay? Actually, not the catch. we have to go back to fundamental theorem of algebra, of calculus, part 2, I think it is, okay, and change this to a dt and a t here, and this now becomes from x0 to x, okay, and then add your c to it. Oh, I'm sorry, we don't need to add the c. Well, yeah, we do. That was your given function there. And when you plug these things in, see what c is equal to. When x is equal to x0, then, yuck, these two limits are the same, right? And that integral becomes 0, so that makes the c, this again feels like you're running in circles, c is equal to y0. Okay? So your solution is y is equal to y0, I'm going to put it in front now, plus the integral from x0 to x g of t dt. That's for those functions you can't integrate. Well, you can always integrate if you integrate numerically. There are packages that will integrate for you. So what you do for any x you put in here, whatever that y0 was, you put that x in here, integrate this from there to there. If you can't integrate it by any analytical means, then integrate it numerically with the given x that you're looking for. Okay. So let's see an example of that. I think it will be. Okay. This is example 5, bottom of page 51. Here's your differential equation. dy dx is equal to e to the minus x squared. Remember, I loved exponential functions, right? Not this one. Okay. And you have initial condition y of 3 is equal to 5. Doesn't look like initial, it looks like some condition. Okay. So, separable variables, right? dy is equal to e to the minus x squared dx, right? First step. Integrate both sides. Fine. This gives you y is equal to. Anyone be able to integrate that? Anyone come up with a technique that might integrate that?
Integration by parts.
Integration by parts. Okay. What would be your parts?
2 and e to the well.
Okay, say that one more time.
Negative x is second power and e to the negative x.
Okay. Okay. It sounds like to me, I'm not sure I'm hearing right, that you might want to do a substitution first. But it's not going to help you much. If you let this be your u, and that's your dv, then when you take a du here, that gets worse, because then you have a minus 2x e to the minus x squared. Okay. So that has that. You do it the other way, that would become your x, 1 dx would be, but then if you try to integrate this, you got your same problem you have here. You don't know how to integrate it. That is one of those functions that's not integrable at all. Now, does it look anywhere sort of a little bit familiar? Like you might have seen something like this before? And you probably avoid this like the plague. Were you going to say something? Say it. A T? Okay. You may be saying the right thing, I just can't hear. Have you ever taken statistics? Most engineers avoid it like the plague, right? Have you taken it?
I was introduced to it.
You were into it? Okay. Okay. You know what it is? This, something like this, not exactly, it gives you your bell curve, your distribution curves. No way really to integrate it, but it's a very useful thing. So it's not this function, but it's one like it. That's non-integral, but you can you can solve it numerically. Okay. So, in other words, we have to do the same trick we just did before. This is going to be the integral of e to the minus t squared dt going from x0 to x. Okay? And plus c. Well, then you plug in y is equal to 5 is equal to, and when you put, and your x0 here would be your 3, and when you plug that in, that goes to 0, so c is equal to 5. Okay? So then your function is y is equal to 5 plus the integral from x0 to, from 3 to x e to the minus t squared dt. Okay. You change variables because your variable in this problem goes up there, so that's a dummy variable over there. You have to have something else. So there's your solution, okay? So to speak, okay? And then the only way you can go from there is to do it numerically. And they have, sometimes you'll find these will have tables of them. If that were actually the one you use for the bell curve, it has a lot more mess in it than just a minus t squared, but that's in there. Then what you do now is just integrate that numerically. And you can find programs that will do that for you, so you don't have to do it yourself. Okay? That finishes, by the way, section 2.2. Homework exercises here. Do any of the odds 1 through 21. The answers to the odd number problems, most of them are in the back. They're not all in the back, most of them are. Then do any of the odds 23 to 27. Do number 29, it's the only one like that. Do either 31 or 33 or both. Do 35. I sort of hate when they do this. Number 37 is find the singular solution of problem 21 and 22, which you would have had to have almost done those, but you can almost look at them and see possibilities there anyway. So you could fiddle with 37 if you want to. Do either 39 or 41 or both. Do 43, it's the only one like that, and I don't think there's a lot you have to do, but, well, maybe, yeah, I guess there is a little bit more. Okay? Either any of the odds 45 to 49, and then the discussion problems only if you just want to dig into it a little bit deeper and think through that. A lot of the discussion problems will not have their answers in the back. If you find some that do, you might want to think of those. Okay? Your good old catenary problem is 57, which is usually a pretty tough problem to do, but if you're interested, you can do it. And then there's computers. I don't know if any of you have access to computer algebra system or Maple or any of the others. If you do, you can try some of those on that. All right. That's it for separable variables. We can always come back and do those if you need. Okay? Let's move on to 2.3. Okay? Now, I would kind of like to take a very quick break. Would y'all mind? So at least get up, stretch, do something. All right. we've talked about linear differential equations, okay? But this seems a bit bizarre. There is a type of differential equation that's called a linear equation, okay? A lot of these we've been doing have been linear, but this is a special class that's called a linear equation, okay? And sometimes these are not separable. And when they're not, there is a new technique, okay? So here is your definition for a linear equation, okay? A first-order differential equation that is of this form, a1 of x dy dx is equal to a0, plus. Got to get it. It wouldn't matter where you wrote it, but they write it with the plus here, okay? Plus a0 of x times your y is equal to some g of x. Okay. Now sure, that is a linear differential equation. Why is it linear? Because your derivative is not raised to any power, and your y is not raised to any power. You can have a coefficient function of x here as long as there's no y's in it. If there was a y in this function, not linear. Okay? If there's any y dependence in this, not linear. If there's any y dependence in that, not linear. If there's any y dependence in that, unless it was to the first power, not linear. Okay? So, as long as these three coefficient functions, these two are coefficients, that's just a constant function, not a constant function, but a function stands alone. As long as those are functions of x alone, no sweat. These can be x to the 15th power. No problem. The y's are linear, okay? This could be sine x, e to the x. It could be any function of x. Totally nonlinear in x, no problem. It needs to be linear in y. This to the first power, that's to the first power, with no other complications, okay? That's obviously a linear differential equation. It's ordinary linear differential equation. Is this necessarily separable? Say again?
Not necessarily.
Not necessarily. So if you have a linear differential equation like this that's not separable, we have to do something else. Okay? You can't do it by separation, or if you can, do it. It could be linear and separable. Do it. Okay? But if it's not separable, then we have other things we have to do. Now, this is not what they call the standard form for a linear differential equation. Okay? This is the most generic form you could have. Okay? To get it into standard form, here's what we do. Divide everything on both sides by this a1 of x. Okay? Now, this is not going to create a problem. Because guess what, folks? If that a1 of x were ever 0, you don't have a differential equation. Right? So there's no problem. You don't have to concern yourself with values of x that would make a1 equal to 0, because if it was, not a differential equation at all. That would be just an equation of y and x. Okay? So you lose the differential equation altogether there. So dividing by that is not a dangerous thing to do. So what do we have then? That goes away. You have dy dx is equal to some new function of x we're going to call p of x. Now, I sort of don't like that they use that, but they do, and I can't do anything about it. And they're going to call this new function of x f of x. Now, why do I not like using a capital P of x there? That's suggestive of being a polynomial function. Guess what? It's defined as a rational function to begin with, so the odds of it being a polynomial function are pretty slim. If it is, fine, no problem. If that original a of x was just a constant, you may have a polynomial function there. But I wish they'd have chosen something, and there, I've done it again. I keep wanting to put the equal sign there, and it's not. That's a plus sign. And you let me get away with it. What were you doing, huh? Okay, that's a plus. Okay, this is your standard form for a linear equation. And you see you can get it by dividing by that leading coefficient function. Because that's only a function of x. That's going to make p only a function of x. But understand, that's not necessarily a polynomial function. It may be, but it's not necessarily. Alpha of x could be anything in the world. Okay? P could be too, whatever you happen to have. So what we're going to look for are solutions of this equation. From now on, for this section, this is going to be called equation 2. Solutions of that equation, the standard form. Okay? On some interval in which both the coefficient functions p of x and alpha of x are continuous. There's a key. Has to be where those are continuous. So therefore, anything that would cause a discontinuity, like a vertical asymptote or something, you can't have it in the interval, of course. Okay, so they have to both be continuous. And I believe differentiable, did they say that? No, they just said continuous. All right. Now, let's look at a couple. dy dx plus 2xy equals 0. Is that a linear function? Yeah, okay. Alpha of x is really simple, 0, and your p of x is a polynomial function, 2x. Okay? Very nice. Okay? How about this one? dy dx is equal to y plus 5. Is that a linear function?
Yes.
It is, but it's not in standard form. To get it in standard form, what would you have to do? Subtract the y from both sides is equal to 5. That is in standard form. There's your p of, the p of x is -1, and the alpha of x is 5. Very nice, simple, constant functions. Okay? Now, is it necessary to do? Okay? This one, you could have solved by separation of variables. Subtract 2xy from both sides, divide by y, multiply by dx. You didn't need to do this. But that is a linear function. That one, yep, multiply by dx, divide by y plus 5. No reason to do what we're going to do. Okay, separation of variable is the way to go. But they're just showing you can have these that are both linear and separable. Okay. Now, how about this one? dy dx plus y is equal to x. Okay? Is that a linear function? Yeah or nay? Yeah. Your p of x is 1, very simple, and your alpha of x is x, very simple. Is that separable? Okay, separate it for me. Multiply dx by both sides, I'll buy that. You have dy plus x plus y dx is equal to x dx. Right? Okay, now what? Divide by dx, it's you right back here again. Right? Okay, is it separable? No, it isn't, because of that plus y. If that was times y, perfect. If it was xy over there, perfect. But that plus in there makes it non-separable. So that kind we're going to have to use using the technique, solve using the techniques this section is going to be talking about. Okay? Now, this method of solution it's one of these things that you would think if they could make this any more complicated, they would, but they think they've got it about as complicated as they can. And I'm not sure you're going to find it all that helpful, but, and this is just to lead to a solution, okay? So let's go back to, and there are parts of me that think, let's just skip all this stuff and cut to the chase and get to the solution. That may, okay, it sounds like an engineer to me, shaking her head, yes. I really am tempted to do that because what we're about to embark in here can get so convoluted, you lose the forest for the trees. I mean, you can't see where you're going because you forget how you got where you got. You know, it's mixing up metaphors like crazy here. I'm going to give it a shot, and if it gets too crazily complicated, then I'm going to stop and say, well, here's what it goes to. Okay? So here's, remember, our standard form. dy dx plus p of x y is equal to f of x. That's our equation 2. We're always going to come back to that pretty much in this section. Okay. Now, here's what they're saying. The method for solving this, it says, hinges on a remarkable fact that the left-hand side here, this thing right here, can be recast into the form of an exact derivative of a product by multiplying both sides of that equation by some special function mu. So that's what we're going to do. So here's a function mu of x. It's just some function of x. We don't know what it is. We're going to multiply it though. Okay? Now, but not yet. Okay. We're going to here's what we want to happen. Okay? I mean, literally this seems like magic. You know what I mean? They're just pulling something out of the air, and here's what they want to happen. They want it to be true that d by dx of the product of mu of x times your y, okay? That product we want to be something very special, okay? Well, let's see what it is. Product rule, right? That would be, I'll use the same, notation they do. What was the product rule tell you that would be? You tell me. Mu prime of x times y. Say that again. Mu of x, y prime. Okay? Now, we know that's true. All right. anytime you multiply mu times y, that's what you're going to get. Okay? And take a derivative of it. All right. Now, they're using the dy dx notation. I think we can get by with this just as well. Now, looking back at what we have here, okay, if you could rewrite this, and I'm going to write it the same way they do, okay, mu of x dy dx, right, would then be equal to, plus y of x d mu dx. Now I'm going to do it the same way they did. Now, I want you to notice something, okay? Here's your dy dx from there, okay? If you were to divide well, let's back that off a bit. Instead of dy dx, we're going to put this thing in, okay? So you have mu of x that's not quite right either. Here's a condition on it. If we could make that d mu dx, if we could make that, force that to be your p of x times y, p of x, make that to be p of x, right? Except they say mu times p of x. And again, this seems like it's so many things they're forcing to happen here. Huh? It's time. Let me just cut to the chase, okay? They go through all this mess. Here's the bottom line. That mu of x that you're going to choose to multiply by is going to be this really weird function. And here, let me write it up here. Let's just get rid of all this because, goodness, that time flew by, didn't it? Okay. Here's what you want that mu of x to be. And we'll pick this up next time, right here. And it seems totally bizarre, but it is totally true. You want the mu of x to be this function. E to the integral of p of x dx. Okay? That seems so bizarre, but that will work. Okay? If you chose that as a function there, that is going to make life a lot easier. So we'll pick up from there next time. And I'm just going to say, yeah, that's exactly where I ended last time. So we'll pick up from there, and we'll see that, hey, it works. It works every time. And we'll realize that once we've done it and seen enough examples of it, say, hey, this really works. Okay, so did we get enough covered for any homework exercises here? I don't think so, because we didn't get to example 1 yet. So we'll pick up and go from there next time. All right. Have a good weekend working on those tests. That'll make it good, won't it? Yeah. And we'll see you then on Tuesday. Okay. Sorry about there at the end. That was trying to find some way to make it easy, and it just isn't like it. Jasmine's still there.